Welcome to this video where we will be exploring flip-flops, one of the most fundamental building blocks in digital electronics. Flip-flops are essential in sequential logic circuits. They act as basic memory elements, storing one bit of data. Unlike combinational logic, where the output depends only on the current input, flip-flops remember past inputs, making them vital in creating devices like counters, registers, and state machines. Flip-flops are essential building blocks in digital circuits used for storing and transferring data. They are bistable devices, meaning they have two stable states, 0 or 1, and can store a single bit of binary information. Some of the key features of flip-flops are: it is bistable. Flip-flops can maintain a stable state, either 0 or 1, until an input signal forces a change. Flip-flops changes states based on clock signals, typically during transitions, rising or falling edges of the clock. Flip-flops can store one bit of data, making them the basic storage unit in sequential circuit like registers, counters, and memory cells. The types of flip-flops are SR flip-flop, which uses set and reset inputs. D flip-flop is often used for data storage due to its simplicity. JK flip-flop, offering versatile functionality, and T flip-flop, used in toggling applications. The SR flip-flop is a synchronous bistable circuit that operates in response to clock signals either on the positive or negative edge of the clock pulse. It has two inputs, a labeled set and reset, and two complementary outputs, Q of t, the current state, and Q dash of t, the complement of the current state. The circuit diagram includes two NAND gates or NOR gates configured such that S and R control the states of the flip-flop. The Q and Q dash outputs are feedback into the circuit, maintaining the state until the next clock transition. When a positive clock transition occurs, S is equal to 0, R is equal to 0, the flip-flop holds its current state, that is, Q remains unchanged. When S is equal to 1, R is equal to 0, the flip-flop sets Q becomes 1. When S is equal to 0, R is equal to 1, the flip-flop resets, the Q becomes 0. When S is equal to 1, R is equal to 1, the condition is typically invalid and should be avoided as it can lead to an indeterminate or misstatable state. The characteristic equation is derived based on the behavior of the SR flip-flop. The D flip-flop is a type of sequential logic circuit that stores and transfers data based on the timing of clock transitions. Here is a breakdown of how it operates. The D flip-flop only responds to either a positive or negative clock transition, meaning it is edge-triggered. This makes the output insensitive to changes in the input during the rest of the clock cycle, unlike the D latch, which is level sensitive and responds as long as the enable signal is active. The single data input labeled as D determines the state of the flip-flop. The output of the flip-flop denoted as q of t as current state and q dash of t its complement state, changes only the active clock transition of the clock pulse. On each positive clock transition in a positive edge triggered flip-flop, the output q of t plus 1 becomes equal to the value present at the data input d at the moment of the clock transition. Thus, it holds the information until the next clock edge. The JK flip-flop is indeed an improvement over the SR flip-flop, addressing one of the SR flip-flop's key issues, the intermediate state when both S and R inputs are high. Here is a more detailed breakdown of the JK flip-flop. The JK flip-flop's inputs J and K modify the SR flip-flop's behavior. This is done by defining S is equal to J Q of T dash. This allows the set operation to be dependent on J and the complement of the present state. R is equal to K dash Q of T. This allows the reset operation to be dependent on K and the present state. The JK flip-flop uses these equations to determine its behavior in response to input combination during the positive or negative edge of the clock signal. Hold state when J is equal to J0 and K is equal to 0, the flip-flop retains its previous state because neither J nor K is active. When J is equal to 0, K is equal to 1, it is said to be a reset state. The flip-flops resets setting Q of t 1 to 0 regardless of the previous state. When J is equal to 1, K is equal to 0, thus it is said to be set state. The flip-flop sets making Q of t plus 1 is equal to 1 regardless of Q of t. When J is equal to 1, K is equal to 1, it is said to be toggle state. This is the key difference from the SR flip-flop. Instead of an intermediate state, the JK flip-flop toggles its output. If Q of t was 0, Q of t 1 becomes 1 and vice versa. The T flip-flop or toggle flip-flop is a simplified version of the JK flip-flop created by connecting the same input T to both inputs J and K of the JK flip-flop. This design allows the T flip-flop to operate with minimum inputs while maintaining the fundamental characteristics of the JK flip-flop. When the clock signal transitions either positive or negative, the D flip-flop evaluates the input T to determine the next state. The input conditions correspond to T is equal to 0, the output Q of T remains unchanged and the state is said to be hold. When T is equal to 1, the output Q of T toggles its state. It is the complement of the present state. The T flip-flop can maintain its current state or toggle to the opposite state based on the value of T at the moment of clock transition. This makes it useful in applications such as counters and frequency dividers where toggling behavior is desired. Applications of flip-flops. Flip-flops are the basic building blocks for memory storage elements such as registers and latches where they store one bit of binary data. In large memory architectures, flip-flops are arranged in arrays to create random access memory and other storage types. Connecting flip-flops in series can form binary counters, which are essential in digital electronics for counting clock pulses. These counters are widely used in timers, digital clocks, and even counting systems. Flip-flops are frequently employed in frequency dividers by toggling between two states with each clock pulse, effectively reducing the clock frequency by a factor of 2. This principle is crucial in phase locked loops and other clock signal applications. A sequence of flip-flops can form a shift register which transfers data from one flip-flop to the next with each clock pulse. This allows for serial to parallel or parallel to serial data conversion and is fundamental in data processing and communication system like UARTs or SPI. Thank you for watching.